over the last few lectures, we have looked at the dynamics of the state of a system. That means that you subject the system to various potentials and then you look at the manner in which the wave function changes when subject to those potentials. Several interesting things can happen. For instance, even in the case of a harmonic oscillator potential, you know that an initial Gaussian continues to be a Gaussian and merely oscillates, preserving its Gaussian form. So this is the kind of statement that you could make about a coherent state of light which is moving in free space, because that too is modeled by a Gaussian wave function. On the other hand, as you depart from coherence, you have seen that the state of the system, for instance the one photon added state, does not preserve its shape or form as it moves. Now we will look at a new class, a new variety of problems, and these come under the title Perturbation Theory. In other words, you look at a system on which there is an external field or force which acts, an external Hamiltonian in general, another Hamiltonian, a perturbing Hamiltonian, has to be added to the original Hamiltonian and therefore the system is affected. Now the external agent which acts on the physical system of concern could be a time dependent Hamiltonian, or it could be guided by a time independent Hamiltonian. So depending on whether the external agent is modeled by a time dependent Hamiltonian or a time independent Hamiltonian, you will do stationary perturbation theory if it is time independent. So stationary perturbation theory, also called the Rayleigh-Schrödinger perturbation theory, Now, if you also have a time dependent Hamiltonian which models the external perturbation, then it is the time dependent perturbation theory. We will first be looking at stationary perturbation theory, and the point here is this: suppose you started with a physical system whose Hamiltonian is given by h naught. This corresponds to the free system which has not been subject to any external agent, and suppose the eigenbases are given by psi n's, but I will also put a superscript there 0 to show that this is the unperturbed eigenbasis, and this is the eigenvalue equation. So for instance, if you took a free harmonic oscillator, h naught would be p squared by a linear harmonic oscillator. H naught is the free Hamiltonian. By free I mean unperturbed Hamiltonian. So let us write unperturbed Hamiltonian. And this, in the case of the linear harmonic oscillator, would be p squared by 2m plus half kx squared, where k is m omega squared. And these would simply be the ket n's, or the Fock states of the oscillator, and the E n zeros would be just n plus half h cross omega, and this is the eigenvalue equation which you know and which you have solved for. we have solved for this set of eigenvalues and the eigenfunctions using the Schrodinger formalism. We have solved for this and shown that these wave functions, that is in the position representation, they would be given by essentially the Hermite polynomials apart from other factors. Now, once you apply an external perturbation, you have a new Hamiltonian, and this Hamiltonian has an H naught plus a perturbing Hamiltonian. When you say stationary perturbation theory, you mean the following thing. First of all, we are dealing with discrete eigenstates. So here you have a set of discrete levels, psi 1 0, psi 2 0, psi 0 0, because n can also take the value 0 in the case of the harmonic oscillator, for instance. So you have a discrete set of levels, and there is this perturbing Hamiltonian, which was some external field possibly, which acted on the oscillator or on the given physical system at some time, and then it has been removed, so that the system now settles down and equilibrates to a new set of discrete levels. So this one's eigenstate are also discrete, a discrete set of levels. So we are doing stationary perturbation theory. In contrast to time dependent perturbation theory. Now this perturbing Hamiltonian, I could just write it as some H prime, but for the sake of bookkeeping, I'd like to introduce a parameter lambda here, and lambda can take values 0 to 1. Basically, if the perturbation is switched off, that's like saying that lambda is 0 and you only have the unperturbed Hamiltonian, the system is not perturbed. Lambda is 1, the perturbation is comparable to H naught. So that's the way it is. Lambda can take any value from 0 to 1, and therefore lambda is the strength of the perturbation. So I write the new Hamiltonian as H naught plus lambda H prime. The very important feature here is the following, that eigenstates of the new Hamiltonian, let me refer to them as psi n, and the new eigenvalues as E sub n psi n. The important thing is that the psi n's are also expandable in terms of this basis set psi n 0. So basically, the perturbation changes psi n 0 by some quantity. I represent this in ket notation. So psi n, the nth level new state, which is an eigenstate of the full Hamiltonian H, is the old nth level plus some delta psi n. Now this delta psi n can be expanded in terms of the old basis. So the perturbation does not change the Hilbert space of the system per se, in the sense that I can retain the old basis set. So delta psi n can really be expanded in terms of the old basis set in this fashion, except that I would assume that the perturbation does not have, in this superposition, does not have a non-zero coefficient corresponding to n. In other words, delta psi n does not have a contribution along the component psi n 0, does not have a component along psi n 0, ket psi n 0. So this is what I have for delta psi n. Now, En itself correspondingly will be the old energy eigenvalue plus an addition delta En because of the perturbation. Now, the aim of perturbation theory is to estimate delta En and delta psi n. In other words, you want the new energy values and you also want the corresponding energy eigenstates. By that I mean the eigenstates and the eigenvalues of the full Hamiltonian H, which includes the free or the unperturbed Hamiltonian plus the perturbation. Now, how do I go about doing this? The aim is to develop a perturbation series. In principle, this is an infinite series, and if it is possible to truncate the series somewhere, effectively, if it is possible to make such an approximation, then it is very good, because I do not have to work with an infinite series, and perturbation is a very effective procedure. The perturbation series can be truncated, and the series itself will be written in powers of the strength lambda. So, for instance, if you are talking about electromagnetism, lambda is usually the parameter E squared, where E is the electric charge by H cross C, and this is 1 by 137. And therefore, if you made a series in powers of lambda, the first term lambda to the 1, that means the first order in the perturbation, has 1 by 137 multiplying things. The next order is 1 by 137 squared, and that is much smaller than 1 by 137, and so on. So, you make an expansion in terms of a quantity whose powers, the strength of the perturbation itself is 1 by 137 in some units, and therefore, higher terms could possibly make lesser contribution, and you can stop the series at some point. You can truncate the series and find out what the wave function is, psi n, and the corresponding En to that order of approximation. On the other hand, it is possible that you will never be able to truncate the series, and then of course perturbation theory itself is not particularly useful. So, we will see specific instances where we can truncate the series and find out what the final wave function and the corresponding eigenvalues are to that approximation. So, the first stage is to write H psi n equals En psi n as H naught plus lambda H prime. Psi n itself is psi n 0 plus delta psi n. This quantity is equal to En 0 plus delta En psi n 0 plus delta psi n. So, that when I expand this, I have H naught psi n 0 plus lambda H prime psi n 0 plus H naught delta psi n plus lambda H prime delta psi n is En 0 psi n 0 plus delta En, which is a number, psi n 0, and then of course I have the last two terms, En 0 delta psi n plus delta En delta psi n. I have merely expanded out things in terms of H naught, H prime, psi n 0, delta psi n, and so on. But I know that H naught psi n 0, I know that this quantity is En 0 psi n 0, and therefore, these two just cancel out. And then what do I have? I have lambda h prime psi n 0 plus h naught delta psi n plus lambda h prime delta psi n. So I might as well just club the two terms and write lambda h prime psi n 0 plus delta psi n, and that is just psi n plus h naught delta psi n. Notice that these two terms just took care of each other, they balanced each other, and therefore I am left with delta E n psi n 0 out there plus E n 0 delta psi n plus delta E n delta psi n. So this is what I have. These two terms balanced out each other. I simply combined lambda h prime ket psi n 0 plus ket delta psi n and wrote that there as the first term. And then I had an h naught delta psi n, and on this side I have a delta E n psi n 0 and E n 0 ket delta psi n plus a delta E n delta psi n. My aim is to find delta E n. I need to find the extra amount, and therefore let me do this. So I have lambda h prime, it's sandwiched between ket psi n and bra psi n 0, that's my first term, plus psi n 0 h naught delta psi n. Now that is delta E n psi n 0 psi n 0, and that is 1 because we have chosen an orthonormal basis, and therefore this inner product is 1, plus E n 0 psi n 0 delta psi n plus delta E n psi n 0 delta psi n. Notice the following. We said that delta psi n, our assumption was that delta psi n is expanded in terms, is a superposition of the psi k zeros, but not psi n 0. And therefore, this is 0. Those two terms drop out, and therefore I have delta E n equals this object psi n 0 lambda h prime psi n plus psi n 0 h naught delta psi n. But notice that h naught psi n 0 is E n 0 psi n 0, and that term therefore drops out because delta psi n does not have a contribution along psi n 0. So that term also drops out, and therefore I have a very simple relation like this. Let me pull the lambda outside, h prime psi n. So this is delta E n. In other words, the effect of the perturbation is to shift the energy value, which was originally E n 0, by an amount delta E n, which is calculable and which is given in this manner. You merely have to find the following scalar quantity. You need to sandwich h prime between psi n and psi n 0. Notice that psi n is the full wave function, whereas psi n 0 was the unperturbed wave function, and h prime is the perturbing Hamiltonian. Lambda h prime is a perturbing Hamiltonian. So here is a very simple way of estimating delta E n, provided I know what psi n is. And as I said, psi n has to be perturbatively estimated. In other words, you write psi n in the following manner as a series in powers of lambda. So psi n is of course psi n 0 if there is no perturbation, plus lambda psi n 1 This is to first order in the perturbation, plus lambda squared psi n 2. This is to second order in the perturbation, and so on. So this is the manner in which psi n is expanded. And you could estimate the wave function perhaps by truncating the series here. That means to first order in the perturbation, or truncating the series here, which means you estimate psi n to second order in the perturbation, and so on. So now when you use that, you just have delta E n is lambda psi n 0, what I have written here, H prime, which is merely the perturbing Hamiltonian, psi n 0 plus lambda psi n 1, and so on, that series. So this is what I have. So let's see what this gives us. Therefore, delta E n is lambda psi n 0 H prime psi n 0. Suppose you initially started with the state psi n 0, what is the probability amplitude that you land up in a final state psi n 0? So that is what this gives you, plus lambda squared psi n 0 H prime psi n 1 plus lambda cubed psi n 0 H prime psi n 2, and so on. So I can always write this in a compact form. Delta E n is summation over s equals 1 to infinity, lambda to the s psi n 0, the unperturbed wave function, the perturbing Hamiltonian, psi n s minus 1. Now this is a good thing for us to know, because if you want to find delta E n to order lambda, that means you set s equals 1, you merely need to know the wave function to a lower order psi n 0. If you wanted to estimate delta E n to the second order, that is lambda squared times something, then you need to know the wave function only to first order, because that is an s minus 1 out there. So basically, if you know psi n 0 and psi n 1, you can estimate delta E n to second order in the perturbation. If you only know psi n 0, you can estimate delta E n to first order in the perturbation, and so on. So the wave function is something you need to know to a lower order, one order lower, in order to find out the correction to the original energy to that order. So that is a nice thing, and therefore I can well write this as summation s equals 1 to infinity lambda to the s E n s, where E n s is precisely this object. So you see, delta E n is also expanded in powers of lambda. You expanded psi n in powers of lambda, and the change delta E n also in powers of lambda. So the total energy will be E n 0. So that is to first order, to 0th order in the perturbation, you have E n 0 plus delta E n, which is written in terms of the first order in lambda times E n 1, and so on. So that is what you have. Now you see, we can feed all these things in and find out what is the change in energy delta E n and what is the change in the wave function delta psi n. So let us see how we go about this. So go back to your equation, and you have h naught plus lambda h prime psi n 0 plus delta psi n is lambda psi n 1 plus lambda squared psi n 2 plus so on, equals E n 0, which was the unperturbed energy, plus lambda E n 1 from here plus lambda squared En 2 plus so on. So, I expand that also as a series in lambda times psi n. So, I can write that as psi n 0 plus lambda psi n 1 plus lambda squared psi n 2 plus so on. So, now let us look at order 0, 0th order. That means only look at terms which have no lambda dependence and equate them. To order 0, what do I have? I have h naught psi n 0 on that side, because every other term contains lambda, is E n 0 psi n 0. This is merely a statement that if you have the unperturbed system, then it is guided by a Hamiltonian h naught, and the basis states, the energy eigenstates are psi n 0, the corresponding energy eigenvalues are E n 0. It is a discrete set of values. Now, if you did first order perturbation theory, that means you compare coefficients to order lambda to the 1 or lambda and equate them in this equation. And what do I have? I have h naught psi n 1 from here plus h prime psi n 0, and that is all I can have here, because I need to just look at terms multiplying lambda, and this comes with lambda squared, lambda cubed, and so on beyond that. So, that the contribution is only from these two terms. But on this side I have E n 0, this is equal to E n 0 psi n 0 cannot make a contribution because you are looking at powers of lambda. So, it is E n 0 psi n 1 out here plus E n 1 psi n 0. So, the first order contribution E n 1, but the wave function is psi n 0. So, this is what I have. I have this equation. If I work to order lambda, that means first order perturbation theory. I can write this better. I can simply group terms and I can write, so this is first order perturbation theory, h naught minus E n 0 psi n 1 equals E n 1 minus h prime psi n 0. So, you see we use lambda for bookkeeping purposes. So, you work to order lambda, lambda squared, lambda cubed, 0th order in lambda, which is the free case, and so on. So, this is the equation that I have. My aim is to find out E n 1, and I have a formula for that, because we have already said that E n 1 out here, put S equals 1. So, that is psi n 0 h prime psi n 0, that is E n 1. So, I know E n 1. H prime is given to me, that is the perturbing Hamiltonian. I know psi n 0, that is the old basis, energy basis with which I began, and my aim is to find out psi n 1. So, there is a very simple way of doing this. So, let us choose k not equal to n and do the following. Minus E n 0 psi k 0 psi n 1 equals E n 1 psi k 0 psi n 0 minus psi k 0 h prime psi n 0. So, I have just used bra psi k 0 on this side. I know what this is. I know that H naught psi k 0 is E k 0 psi k 0. Therefore, E k 0 psi k 0 psi n 1, and they can have a non-zero overlap. Remember that psi n 1 is the wave function to first order in the perturbation. So, it is the first order contribution to delta psi n, and a very crucial input was this, that delta psi n did not have a contribution along psi n 0, and we have selected k not equal to n. So, delta psi n, when expanded in terms of the basis set, the psi k zeros, it would have a component along psi k 0 in general, provided k is not equal to n, and that is what I have used here. This is in general non-zero. So, minus E n 0, same thing out there, psi k 0 psi n 1. This is 0 because we have chosen k not equal to n, and since this is the eigenbasis of the unperturbed Hamiltonian and they are mutually orthogonal. So, this term does not contribute, but I have equals minus psi k 0 h prime psi n 0. So, you see once more what figures is merely this matrix element of H prime between the unperturbed state psi n 0 and psi k 0 in order to estimate things in the first order of the perturbation. I need to know only the wave function to 0th order in the perturbation. So, I need to put down delta E n. We have already shown that that is summation s is equal to 1 to infinity lambda to the s E n s, where E n to any order is really this object. It is psi n 0 h prime psi n s minus 1. So, these are important things that we have already shown. So, that is the way it is. So, now going back to this equation, we are trying to estimate the wave function and the energy eigenvalues to first order in the perturbation, and we have an equation of this form, and therefore, I can write, so first order perturbation so I have psi k 0 h prime psi n 0 equals E n 0 minus E k 0 times a non-vanishing quantity in general, which is psi k 0 psi n 1 inner product, and this is what I have. So, I can well write it in the following fashion. Remember, I need to find out psi n 1. This is the quantity ket psi n 1 that I need to estimate. So, take this matrix element and divide it by this number. The energy corresponding to the kth level, the energy corresponding to the nth level, and n is not equal to k. That is the way we have taken things. So, if I want to estimate ket psi n 1, all I have to do is do a summation k not equal to n psi k 0 psi k 0 psi n 1. This object is summation k not equal to n psi k 0 psi k 0 h prime psi n 0 by E n 0 minus E k 0. In And this is very interesting because since k is not equal to n and you are summing over the k's, look at this part. This object should simply be equal to identity if I had also put k equals n. So therefore, this reduces to identity minus the projector onto get psi n. But because psi n 1 has no component along psi n 0, I have psi n 1 equals summation k not equal to n, and here unfortunately I cannot simply do that summation because there is an ek out here, and this is a matrix element which I will call h prime n k n, but for the moment let me just write it down. Psi k 0, this is what I have, divided by E n 0 minus E k 0. So this summation extends all over, and this is what I have. All I need to know is this matrix element which I will call h prime k n. It is the k nth element of the matrix h prime. H prime is an operator, and if you give a matrix representation, this is clearly the k nth element of the matrix h prime. And I need to know the unperturbed wave functions, and I sum over all k's not equal to n, and I know that this won't blow up because n is not equal to k, and this is the manner in which I find psi n 1. So I have psi n 1 is summation k not equal to n h prime k n psi k 0 divided by E n 0 minus E k 0, and E n to first order is something that I know. E n to first order is psi n 0 h prime psi n 0. So you see, this formalism turns out to be extremely useful because to determine the energy values and the wave functions to first order, I only need to know the energy values and the wave functions to 0th order. So if I now compared, if I did second order perturbation theory and I took that huge expression that we had earlier and I equate coefficients of lambda, I equate terms with coefficient lambda squared, then I will find that the aim would be to estimate psi n to second order and E n to second order in that case, and all I would need would be the wave function to 0th order and first order, which I would have estimated already. The 0th order wave functions I know, they are the free Hamiltonian wave functions, eigenstates, and then the first order wave function which I would have gotten from here. Similarly, I would need to know E n zeros, that entire set, and the psi n zeros. So you see, if I know the energy 0th order and first order, and I know the wave function 0th order and first order, I know the energy and the wave function to second order, and so on. So I need to know these values to an order less than what I wish to determine, and therefore it becomes some kind of a recursion relation where I feed in the 0th order values and get the first order values, feed in the first order values and get the second order values, and so on. Now these are the results that I get for the contribution to first order to the energy and to the wave function because of the perturbation. So let us try to illustrate this first. Let us use these formulae. Let us try to illustrate this with a very simple example, the linear harmonic oscillator, where I add a perturbation such that the harmonic nature is still maintained. So example, the linear harmonic oscillator, the simplest example I can think of. So you know that H naught is p squared by 2m plus half k x squared. So k is m omega squared. And I give you an h prime. Let me set lambda equals 1. Then h prime, let me say, is b by 2 x squared. So since this is also quadratic in x, the harmonic nature is going to be maintained. There is no anharmonicity in this problem. So this is h prime. Lambda was set equal to 1. So I wish to find out the new wave function. I know the old wave functions. I know that the set psi n0 in my notation is simply ket n taking value 0, 1, 2, 3, etc. These are the eigenstates of the free Hamiltonian or the unperturbed Hamiltonian. So given that, let me first estimate En1, the first order contribution to the energy. Now to first order, the total energy will be En0, which I know is n plus half h cross omega, plus lambda En1, but I have set lambda equals 1 in this problem. So this is going to be the contribution to energy to first order. And similarly, psi n to first order would be psi n0, which is simply ket n in my usual notation, plus the contribution psi n1, which I will calculate using this. All I need is the matrix element of the perturbing Hamiltonian, the knth matrix element of the perturbing Hamiltonian. The Hamiltonian is given to me, so I can well do this calculation. So this is a very simple illustrative example to show the power of perturbation theory. So let's look at En1. In our example, this is simply n h prime n, and since b is a constant, I pull that out, and x squared has to be written, and I prefer to write it in terms of the ladder operators a and a dagger. You will recall that x is root of h cross by m omega, a plus a dagger by root 2. Let me remind you that this is what provides the length scale in the problem. So x squared was a half h cross by m omega, a plus a dagger the whole squared, and if you keep the ordering right, this is what it is. And therefore En1 is simply b by 4 h cross by m omega n a squared plus a dagger squared plus 2 a dagger a plus 1 n. Now since I had written my h naught, h naught as p squared by 2m plus half k x squared. So let's see, k is really m omega squared, and I seem to want m omega all the time. So m omega is k by omega, and therefore I can write this as b by 4 h cross omega by k because of this reason. So let's see where this takes us. Look at this. A squared is a lowering operator. So when a squared acts on n, brings it down to, first time it acts, a acts on n to take it down to get n minus 1, and then the a again, and that makes it get n minus 2, and since they are orthogonal states, you do not get a contribution from this term, which is the expectation value of a squared in the state n. Similarly, from a dagger squared, you do not get a contribution. However, you get a contribution from a dagger a, because you would recall that ket n is an eigenstate of a dagger a with eigenvalue n. And therefore, you have En1 is equal to b by 4k h cross omega twice n from here plus 1 from there. So this can be written as b by 2k h cross omega n plus half. So this is what I have for En1, and therefore En to first order is En0, which is n plus half h cross omega, plus En1. So it is simply b by 2k plus 1 n plus half h cross omega. So this is what I have. So this is my value of energy inclusive of first order corrections because of the perturbation. So now let's go ahead and estimate psi n1. This involves h prime k n psi k 0, and let's find out that matrix element. So let me write this somewhere. For the harmonic oscillator problem, I have found out En. So let's just say En1 is b by 2k times n plus half h cross omega. This is what I have. Now as far as psi n1 is concerned, I need to do the following thing. The wave function to first order in the perturbation is summation k not equal to n. I need the matrix element h prime k n, which is k b by 2 x squared n psi k 0, which is k so that is what I have there, divided by En0 minus Ek0. Recall that En0 is n plus half h cross omega, and Ek0 is k plus half h cross omega. So you just have an n minus k, and k is not equal to n h cross omega. So this object can well be written once more as b by 4 k h cross omega summation. This k is not to be confused with that k. This is capital K, which was m omega squared. If you wish, I am willing to write this as p not equal to n in this fashion. And therefore, we just have b by 4 k h cross omega summation over p not equal to n. This k is m omega squared. And then you have p a squared plus a dagger squared plus 2 a dagger a plus 1 n p by n minus p h cross omega. So the h cross omega cancels out, and I have a b by 4k this. Now this is a nice thing to do because certain terms make a contribution. I have summation p not equal to n. Look at the first term. The first term brings out a root n ket n minus 1, root n minus 1 ket n minus 2, delta p n minus 2. The denominator is p is equal to n minus 2. That is the first term. The second term gives me summation p not equal to n. The second term gives me a dagger on root n, gives me root n plus 1 ket n plus 1. Once more gives me root n plus 2 ket n plus 2. So that is a delta p n plus 2. The denominator is n minus n plus 2. That is the second term. The third term cannot make a contribution because a dagger a on ket n gives me ket n, and this gives me a delta n p, but you have to sum over all p not equal to n. Similarly, the fourth term does not make a contribution, and of course I have ket p. So this is what I have. Now, this is easy to simplify, and all I get is the following. I can remove the summation and the delta sign, and therefore, the p is to be replaced by n minus 2. So, I have psi n1, this is the first order contribution to the wave function, is root n minus 1. The denominator is a 2. Of course, I have a b by 4k, so I have a b by 8k. And since p is replaced by n minus 2, I have ket n minus 2. That's the first term coming from here. The second term has a p replaced by n plus 2, and therefore that gives me a minus 2. So, let me put a relative negative sign, minus b by 8k again, and I have a root of n plus 1, root of n plus 2, ket n plus 2. So, this is psi n1. So, I have found out the contribution to energy and the contribution to the wave function in first order perturbation theory. If I were looking at a harmonic oscillator with a harmonic perturbation, in the sense that the perturbation is also a quadratic perturbation. So, you see the contribution to first order does not come from psi n0, it does not come from ket n, it comes from ket n minus 2 and it comes from ket n plus 2, which is consistent with the fact that our delta psi n did not have a component along psi n0. So, this is what I have in first order perturbation. So, here is the estimate of the energy, and here is the estimate of the changed wave function, and I have just demonstrated first order perturbation theory to you. We will look at second order perturbation theory and harmonicity and so on in subsequent lectures.